Hello, welcome to the second video in this series where I'm solving all of the A-level Edexcel maths questions from the Year 2 textbook. So we're focusing on differentiation today, 9.2, which is differentiating exponentials and logs. So before we get into it, if you haven't already, please like and subscribe and check out the Discord link in the description down below to join the Bridge community where you can get extra help with your A-level maths, have more input on these videos, and just join a community of people trying to do well just like you are. Okay, let's get right into it. So here we go. So all of these questions are going to be differentiating functions that either have an exponent, which is the x, or they're going to look something like log of x. But it's the standard type of differentiation question where we're going to have to be finding tangents and normals and all that jazz. So, okay. The first question, it wants us to differentiate y is 2 to the power of x plus 2 to the power of minus x at a point. So, okay, before we do that, how do we differentiate y is 2 to the power of x? Well, we know how to differentiate y is e to the kx, right? That goes to ke to the kx. So this is what you're given. Now, how do we go from this derivative into differentiating that? And the key is that you can write any exponential that doesn't have e as a base in terms of e. So let's just do that quickly just so we can get the right answer for this. So 2 to the power of x, that is the same as e to the power of the natural log of 2 to the power of x. E and the natural log are the inverse of each other. So this is just exactly the same thing. So I could probably put an identity here. Right. So now using the properties of logs, I can take that x and put it at the front. So that's going to give me e to the x natural log of 2. And now this is just a constant. Right, so we are now in this format here. So if I differentiate this, that's going to go to the natural log of 2 e to the x ln 2, or since this thing here is just what we started with, this is just 2 to the power of x. So this is ln 2 times 2 to the x. Okay, so that's the general formula for differentiating a function where it doesn't have e as the base. We take the natural log of the number and put it on the outside. So for our question then, y is 2 to the x plus 2 to the minus x. Yeah. We know how to differentiate each of the terms now. So dy by dx is going to be ln 2 times 2 to the x plus ln 2 times 2 to the minus x. Right. Okay, so now that we've got that, what do we want to do with this? We've got the point 2 and 17 over 4. Okay, so it wants us to find the tangent there, so we should probably find out what the gradient is when x is 2. So that's going to give us ln 2 times 2 to the 2 plus ln 2 times 2 to the minus 2. Okay, so that's 4 ln 2 and then plus a quarter ln of 2. Okay, so that's going to be 17 over 4 natural log of 2. That's the value. So this is going to be, if we're looking for a tangent, that's going to be the gradient of that line. Okay, so let's write out the general equation now for the tangent. Well, it's just a straight line, so it's going to be y is equal to mx plus c, where m is the gradient that we've just worked out. So y has to be 17 over 4 ln 2 plus c. This is our tangent line. So what remains is we need to work out what c is. And that's easy to do because we know that the other point on the curve is 17 over 4. So we have 17 over 4. And sorry, I've missed an x here. So when I plug in x is 2, I get that 17 over 4 must be equal to 17 over 4 ln 2 times 2 plus c. Okay, so if I take this away to the other side, I'm going to get that c is equal to 17 over 4 minus 17 over 2 ln 2, where I've multiplied this into here. So you could, I guess, factorize this a little bit if you wanted to, but we don't really need to. So let me just make a new page. So that's our value for c. Now plugging that in now, I'm going to get y is equal to 17 over 4 ln 2 x plus 17 over 4 minus 17 over 2 ln 2. Okay. So there we go, that's the equation of our tangent. So this just relied on us knowing how to differentiate 2 to the power of x. And again, that just follows straight from how you differentiate e to the x. Okay, next question. Got quite a few questions here today. Let's make that a bit bigger. Right. So question 5. A curve has the equation y is e to the 2x minus the natural log of x. Show that the equation of the tangent at the point with x coordinate 1 is given by this. Okay, so we don't have to differentiate anything too weird here, it's just standard exponentials and logs. So remembering that the natural log of x differentiates to 1 over x. And e to the kx as before, that differentiates to k e to the kx. So they're easy derivatives to do. It's simply about applying the same rules that we have the entire time for working out equations of tangents. So again, if we want the equation of the tangent, we need to know the gradient at that point. If we want to know the gradient, you need to differentiate. So that's what we're going to do. So if y is equal to e to the 2x minus ln x, dy by dx is going to be equal to 2e to the 2x minus 1 over x. Okay. Where are we trying to find the gradient? Where the x coordinate is 1. Okay, so let's quickly just find out what the overall point is. So it's going to be 1, and to find out what the y value is, we just need to plug 1 into here, which gives us e to the 2 minus natural log of 1 which you should remember this is 0. So our y coordinate is just e squared. Okay, let's keep a note of that. So what is our gradient at the x value being 1? It's going to be 2. We're just going to plug it into our derivative. It's going to be 2e to the 2 lots of 1 minus 1 over 1. So that's 2e squared minus 1. So this is our gradient. Now, does that pop up? Yes, it does. It's in our formula already. So this is correct. It's good when they give you these show that questions, you can at least know if you're on the right track. So, okay. That means for our tangent, if this is the gradient, then the equation of the line, well, it's going to take the form y is mx plus c, as always. We now know what our m is. It's just given by what we just worked out. So we're going to have y is equal to 2e squared minus 1x plus c. So once again, it remains to work out the c, the y-intercept. How do we do that? Well, we just need to use another point on the line, or we need to use the values that occur at a certain point, and we have this one here. So we know that when x is 1, the y value is e squared. So let's put that in. So when x is 1, y is e squared. So e squared is equal to 2e squared minus 1, lots of 1. So that's me substituting in x is 1 plus c. So if I put this over to the side, I'm going to get c is equal to e squared minus 2e squared, and then if I keep it in brackets for now, so I've minused that off, which is going to give me 1 minus e squared. Okay, I've minused the minus 1, that gives me a plus 1. So that's our c value. So now we've got all the bits we need. That means the general equation of the line, substituting that back in, is going to be y is equal to 2e squared minus 1 x plus c, and c is given by what we just worked out, plus 1 minus e squared. Okay, let's just check that was what you wanted. And it is, yeah, I've written it slightly different, but it's exactly the same thing. Okay, great. Right, so on to question 7. And what this is 9.2, if I didn't mention already. So 9.2, differentiating exponentials and logs, and this exercise and 9b, where you can find these questions. So question 7 is a problem solving question. So let's have a look at that. The population of Cambridge was 37,000 in 1900 and was about 109,000 in 2000. Given that the population P at time t years after 1900 can be modelled using the equation P is equal to P naught k to the power of t, find the values of P naught and k. Okay, so it's a problem solving question. We need to think about it a little bit more, but this is pretty standard for how you see the modelling questions pan out with exponentials. They all look something like this. So, okay, let's see if we can do that. So we know that it was 37,000 in 1900. So t is the number of years that we're interested in, and P is the population. Okay, so it's t years after 1900, sorry, so that's important. So that means that for our value at 1900, t is equal to 0. So we know that from this, p is equal to p naught k to the power of t, that when t is 0, p is 37,000. So I can write 37,000 is equal to p naught k to the 0. And k to the 0 is equal to 1, right? So p naught then is 37,000, which makes sense. Because p naught is the initial population. Great, okay. So to find k, we need to use the other bit of information. So we know that it was 109,000 in 2000. So in the year 2000, t is going to be equal to 100. So we can substitute in, p is 109,000. That's going to be equal to p naught k to the 100. But we now know what p naught is. We've just worked it out. It's 37,000. So 109,000 is equal to 37,000 times k to the power of 100. And so we can at least work out what k to the power of 100 is now if we divide through on our calculator. So if I can find it, yeah. So 109,000 divided by 37,000. Okay, it's not that nice. So that's going to give me, I'll leave it as 109 over 37 is equal to k to the power of 100. And it hasn't asked us to give it in any nice form, so I'm going to have to do the 100th roots now of this number. So if I do that, you can do it on your calculator. K is equal to 109 over 37 to the 1 over 100, or the 100th root. So let me do that. 109 over 37 to the power of 1 over 100. So that gives me k is 1.01 to 3 significant figures. Okay. Now, if you do find a mistake in any of these videos, please let me know in the comments. I'm doing all of these on first sight, so it is possible that I make a mistake somewhere. Alright, so what have we got next then? So now it wants us to evaluate the derivative of p with respect to t in the year 2000. So let's do that now. We can first write out what our full formula is now. It's going to be p is p naught, which is 37,000, times k, which is about 1.01, to the power of t. Okay, so we want to work it out. It said in the year 2000. So again, that's when t is equal to 100, and we need to differentiate p now. So as we saw in the previous question, we can differentiate these exponentials pretty easily. So it's going to give us 37,000 times. Now when we differentiate this, we get the natural log of the base times the thing itself. Okay. So we're going to get times the natural log of 1.01 times 1.01 to the t. So if we now evaluate it at t is 100, we're going to get 37,000 times the natural log of 1.01 times 1.01 to the power of 100. And we actually don't need to work this out properly because we know what k to the power of 100 is already. It was here. And this 1.01 is just k. So we know that this is 109 over 37. So that's nice. It means we can be more exact. So that's going to give us, if we put that in a calculator, 37,000 times the natural log of 1.01 times 109 over 37. So that gives me 1084.586. So to three significant figures, it's going to give me 1090. Okay. So continuing. Interpret your answer to part B in the context of the model. So what is our model? Our model is modelling population growth. So P is equal to P naught K to the T. So what we had is this was the initial population, wasn't it? And that was at time 0. So this was in the year 1900. K is sort of the rate of increase. So we know our K is 1.01, which means with every year it gets 1.01 times bigger. If that's a little bit confusing, imagine if K was equal to 2, then our rate would be a doubling. So every year we would double the size of our population. So obviously we're not doing that, it's a lot less. So what is this telling us? Well, we want to say, what does dp dt tell us? Well, it tells us precisely the rate of change of the population with respect to time. That is literally what the derivative is telling us. Always. It's telling us the rate of change of this variable with respect to this variable. Okay, so we've just worked out that it's 1090, so it means that at that point in time, i.e. 100 years, the rate of change of the population, or the population is changing by 1090. That's how quickly we're increasing it. Okay. Right, so that's it for that question. Again, that's not so typical as an exam question. That's a problem-solving question, but all of the right ideas are still in there. But let's go on to the next one. Okay, so this one should be pretty straightforward. All we've got to do is explain where the student is going wrong. Okay, they're trying to differentiate ln kx. The student writes y equals ln of kx, so dy by dx equals k natural log of kx. Okay, so what have they done here? Well, we know that when you differentiate logs, you don't end up with a log coming back, right? Just differentiating the natural log gives you 1 over x. So what they've accidentally done is they have accidentally treated ln of kx as, or like, e to the kx. Because you know that e to the kx would differentiate to k lots of the thing itself. So what is the correct derivative? Well, if y is equal to the natural log of kx, then dy by dx is equal to, well, we can use the chain rule. So it's 1 over, we know it's 1 over the argument, times by the derivative of the argument. And the derivative of kx with respect to x is just k. So that just gives us 1 over x. And this is the special thing about logs, is that ln of kx, or let me just say ln of x, ln of 2x, and whatever, they all differentiate to 1 over x. So they all have the same rate of change with respect to the x-axis. So that was a pretty quick question. This is what we should get for the answer. Okay. Right, moving on. So, question 9. So this is a general version of what I talked about right at the very start. So at the very start, I looked at 2 to the x, and I showed you that that should differentiate to ln 2 to the x. So here, it's asking us to show that a to the kx goes to the thing itself, a to the kx, times k times the natural log of a. So very similar, so we've still got that there, and this corresponds to this, but we obviously have this extra k turning up here, which again will be due to some sort of chain rule happening. The way to prove it is to do the exact same thing as I did before. So let's let y equal a to the kx. Or maybe we don't need to do that yet. Let's just consider a to the kx, and let's write it in a nicer fashion as I did with the 2 to the x beforehand. So a to the kx is just e to the natural log of a to the kx, right? Because this does nothing. E to the natural log of anything is just the thing inside of the natural log. We're just writing it in a nice way so that we can now use properties of logs to bring that out to the front. So that's going to give us e to the kx natural log of a. And remember, this is now just a constant. Or so let me write it like this. Maybe x times k. So this whole thing here is the constant. So if we let y equal a to the kx, then that means that we have actually y is equal to e to the, you write it this way around, k natural log of a x. So dy by dx is going to be equal to, and now we just use the general rule that we know for exponentials, for e to the x, sorry. So that's going to differentiate to the constant k ln a times the thing itself. Great. And remember again, this thing here is just a to the kx. Right, I went through this whole process to get to this, which is just here. Sorry. So this is just a to the kx. So we're done. So there we go. dy by dx is equal to k natural log of a times a to the kx as required. And yeah, we obviously used this assumption here, where we assumed that the derivative of e to the kx is k e to the kx. Okay, so on to the next one. Question 10. We're going to have f of x is e to the 2x minus the natural log of x squared plus 4, with x being greater than 0. First, it wants us to find the derivative. So, okay, f of x is e to the 2x minus natural log of x squared plus 4. So, what you can make the mistake of doing here is trying to use the chain rule on the natural log of x squared, but it is actually completely unnecessary to do that. So first, we notice, using the powers of logs, that if we have an exponent inside of the log, it can come out to the front. So let's do that first. We're going to get f of x is e to the 2x minus 2 natural log of x plus 4. Okay, so now let's differentiate. We're going to get f dash of x is 2e to the 2x minus 2 over x, and the 4 goes to nothing. Okay, so it was much easier to just turn this ln of x squared into 2 ln x. Okay, so that's part A done. Show the curve with equation y equals f of x has a gradient of 2 at point P. The x coordinate of P is A. Sorry, that hasn't asked me to show that. The curve with equation y equals f of x has a gradient of 2 at point P. The x coordinate of P is A. Show that A lots of e to the 2a minus 1 is 1. Okay, so if we don't know exactly what to do here, the best thing we can do is just start using the information that it's given us. So it's telling us that we have a gradient of 2 at point P. Well, we have the gradient function now. It is here. Point P has an x coordinate A. So let's plug in what the gradient is at A. So the gradient at A is simply substituting A for x in our formula here. So that's 2e to the 2a minus 2 over A. And it just told us that the gradient is 2 here. So this must be equal to 2. Now, it's asking us to show an equation in terms of A, which is exactly what we have here. It just doesn't quite look like what they want at the moment. So we need to make it look like lots of e to the 2a minus 1. So why don't we? It's clearly not very helpful us having the a down here. So what I'm going to do is multiply everything by a. That's going to give me 2a e to the 2a minus 2 is equal to 2a. Let's just divide everything by 2 as well whilst we're at it. So we have a to the 2a minus 1 is equal to a. Okay, so we're very close now. So clearly the 1 needs to go to the other side. So this is going to be a e to the 2a, and let's put this a onto this side. So we're going to get minus a is equal to 1. And to finish it off, we just need to factorise. So I'm going to pull out the a and we're going to have an e to the 2a minus 1 is equal to 1. Done. Okay, great. So yeah, if you find something like this and you can't quite see how to get to the solution, just start doing the stuff that it's told you to do. There's nothing else you can really do apart from just plugging a into our derivative and see what happens. Okay. Moving on, let's go to question 11. So a curve C has equation y is equal to 5 sine of 3x plus 2 cos of 3x for x between minus pi and pi. What we want to do is show that the point P, 0, 2, lies on C. Okay, that should be pretty straightforward. All we need to do is substitute x being 0 into here and make sure that the y value is 2. So let's do that. So y, well, let's say when x is 0, y is equal to 5 times sine of 0 plus 2 times cos of 0. Sine of 0 is 0, cos of 0 is 1, so this is going to give us 2. So the point P, 0, 2 does in fact lie on C. Alright, so now we need to do what is more typical in the differentiation questions. They want us to find a normal. Sorry, there we go. So they want us to find a normal to the curve C at P. So let's think about that. Find the normal to C at P. If you want to find the normal, in order to do that, you need to know what the gradient of the tangent is, so you can take the reciprocal of that. So we need the gradient at point P. To do that, we need to differentiate. This is the sort of method you want to follow. What do I know, and then what do I want to find out? Okay, so we need to find out the gradient first. So let's differentiate. So I'll just copy this. So the derivative here, we've not actually had to use any exponentials in this question. So that's okay. We're going to find dy by dx is equal to, so again we just need to use the chain rule here. So I'm going to get 3 times 5, 15 cos of 3x minus 6 sine of 3x. Okay, where I've just had that 3 multiplied by the 2 and the 3 multiplied by the 5 to get these numbers here. So at point P, the x value is 0. So dy by dx of x being 0 is 15 lots of cos 0 minus 6 sine of 0. So this goes to 0. This is equal to 1. So our derivative, the value is 15. So that is the gradient. Let me add a page. That is the gradient of our function at the point P. So the gradient of the normal is going to be negative 1 over 15, right? The negative reciprocal. Therefore, the equation of the normal, well, it's just a straight line again with this gradient. So it takes the form y is mx plus c, where this is m. So we're going to have y is equal to negative 1 over 15 lots of x plus c. And to work out what the c is, we just need to use the rest of our point P, which is 0, 2. That is on this line. So when y is 2, we're going to get negative 1 over 15 lots of 0 plus c. So that gives us that c must be 2. Therefore, overall, the equation of our normal is y is negative 1 over 15 x plus 2. Okay. So I think we're getting there now. That's question 11. I think we should only have 2 more left. Question 12. Okay, so finally back onto some exponential questions again. Alright, so again we've got the point P lies on the curve with that equation, and the x-coordinate of P is 1. Find an equation of the normal to the curve at point P in the form y equals ax plus b, where a and b are constants to be found in exact form. So this really is the same as before. It's just that our function is slightly different. But the process should be exactly the same. So, okay. The x-coordinate of P is 1. So P is 1. Let's find the y-coordinate now before we move on. So y is going to be 2 times 3 to the 4 times 1, which is 4. So this is 81. So 2 lots of that should be 162. So P has values 1 and 162. Okay. So let's continue. We want to find the equation of the normal. So again, we need to know the gradient so we can then take the reciprocal, the negative reciprocal. So to do that, we need to differentiate. So we differentiate to find the gradient. So you see the process here is exactly the same every time. So we're going to get dy by dx. So maybe we should be a bit careful here. So let me just write it out in full. So y is equal to 2 lots of 3 to the 4x. Remember before we've already shown what the derivative of this is. If you recall, we had if y is equal to a to the kx, dy by dx is equal to k natural log of a times a to the kx. That's what we proved in one of the other questions already. So let's use that here. A is just 3, k is 4. So we're going to get y dy by dx is equal to 2 times, now we're going to get the k coming down, which is 4, times the natural log of the base, which is 3, times 3 to the 4x. Okay, so more compactly, 8 ln 3 times 3 to the 4x. Okay. So that's our derivative. We can now find the gradient. So all we know is that the x-coordinate is 1, so we can put that in. So we want to find it at point P. So at x equals 1, the gradient is 8 times the natural log of 3 times 3 to the power of 4. Right, where I've just substituted in x is 1 here. So I guess I can put that in my calculator and work out what it actually is. It's 81 times 8. So we need to keep it in exact form, so we have to keep this natural log as it is, but that's going to give us 648 natural log of 3. Okay, so that is the gradient at the point. Remember, again, we want the normal. So the gradient of the normal is the negative reciprocal. So that's going to be negative 1 over 648 natural log of 3. So it's getting a little bit messy now, but that's okay. The equation of the line is then going to be given by standard y is equal to mx plus c. Now I know they've written a and b in their equation, so maybe we can just write it like that. So a is our gradient. So we already know that a is equal to negative 1 over 648 ln 3. To work out b, we need to plug in that we have our point P on this line. So P is 1 and 162. So if we know that y is equal to this x plus b, to work out b we need to plug in x equals 1. So we should get 162 is minus 1 over 648 natural log of 3. Plugging in x equals 1 just leaves that as it is, and we're going to get a plus b. Which means that if I move this to the other side, we're going to get b is equal to 162 plus 1 over 648 ln 3. So it looks pretty messy here, but hopefully that's all okay. But again, these are all the same question really. We're just doing the same thing over and over again. We're differentiating, we're finding the gradient, we're substituting in the point, and we're getting the answer. Is that all it wanted us to do? Yeah. So, finally, the last question is going to be the challenge. And what have we got here? So we've got a curve with equation y is equal to e to the 4x minus 5x. Find the equation of the tangent to C that is parallel to the line y is equal to 3x plus 4. Okay, so it's a little bit more complicated this time, because instead of just finding the equation at a point, we're having to actually kind of find the point where we have a certain gradient. So we want to find the equation of the tangent to C that is parallel to that line. So if it's parallel to this, what does that mean? It means that the gradient of our line that we're trying to find must be 3. So that's probably a good place to start. That's what we know. Why don't we just try and find out where our gradient could be 3 on our curve? So how do we do that? Well, we need to differentiate, don't we? So we're going to get dy by dx is equal to 4e to the 4x minus 5. And we want to know, where does the gradient equal 3? So let's set it equal to 3. And then we're going to solve for x. So we know that 4e to the 4x minus 5 is equal to 3. That's going to give us 4e to the 4x is equal to 8, which means e to the 4x is equal to 2. And solving exponential equations like this is easy. We just have to take logs, right? Natural logs. So we're going to get, let's do it, I'll do it like this first. The natural log of e to the 4x is equal to the natural log of 2. The natural log of e to the power of something is just the thing in the power. So that's going to give us 4x is ln of 2. Okay, which means that x is equal to 1/4 natural log of 2. Okay, so we're not done, but we've come quite far. What have we just worked out? We've worked out that the point at which we have a gradient of 3 on our curve is when x is 3. So if we're going to work out the tangent, the equation of the tangent there, we're going to need to know another point. We need to know what the y value is. Well, that's easy enough to do because we have the equation of the curve. So we can work out the y value. So the y value is given by when we plug in to our equation, that is y is equal to e to the 4x minus 5x. So when x is equal to what we had up there, 1/4 ln 2, what is y? Well, y is going to be e to the 4 times 1/4 ln 2 minus 5/4 ln 2. So this cancels out nicely. The 4 and the quarter cancel out to 1. And then we're just going to have an e to the power of natural log of 2. So this is just 2. You can check that for yourself if you're not convinced. So y is going to be 2 minus 5/4 ln 2. So this is just the other value of the point on the curve. It's the y value. So the point of the curve that we're interested in is 1/4 natural log of 2 and then 2 minus 5/4 natural log of 2. Okay, so that's helpful because now we can actually work out what the c value is going to be on our tangent line. So let's just recap. What did we want to do? We wanted to find the equation of the tangent to c that is parallel to that line. So what did we do? We worked out where on our curve do we actually have something that's got a gradient of 3, and we found the x value for that. So now we just need to find out the equation of the tangent. So we're back on normal territory now. So y, the equation of the tangent, is going to be of the form y is mx plus c. Now we know that m is our gradient, right? So we worked that out already. Oh well, we haven't worked it out, but we know it has to be 3, right? Because that was by intention. So we know our equation of the tangent has the form y is 3x plus c. Now to work out c, we need to use a point on the line, which we have here. That's what the whole point of that was. So we can now say that when x is 1/4 ln 2, y is 2 minus 5/4 ln 2. That's equal to 3 lots of the x value plus c. So to work out what c is, we just need to put this stuff over to this side. Okay, so that's going to give us 2 minus 5/4 ln 2 minus 3/4 ln of 2 is equal to c. So let me put that together. 2 minus 8/4, which is 2, ln 2 is c. Okay, so putting that all together, we now have that our equation of the tangent must be y is equal to 3x plus 2 minus 2 natural log of 2. Okay, so hopefully that makes sense. That was a little bit more involved. Of course, it's the challenge question, but if it's going to be parallel, of course it has to be a 3x in there. So the real goal of that question was to find out how do we work out what c is. And to do that, you need a point on the curve. And to find that point, what we had to do was take the derivative here and set it equal to 3. We wanted to know where are we equal to 3. Where does the gradient equal 3? And then we had to solve for the x value, which we did. Once you have the x value, you can work out the y value because it's just on our curve. And once you have both of them, it's the exact same process as before to work out the equation of a tangent. Okay. Right, so that is all of the questions from exercise 9b in the Year 2 Edexcel Pure Maths textbook. So I'll leave it there for this video. Thank you very much for watching. If you'd like to see more of this, please again like and subscribe. Make sure to join the Discord in the description. And if you would like any private tuition, you can make inquiries for that via email, which is also in the description down below. I'm going to be coming back with more videos on the differentiation topic. We're going to be covering 9.3, 9.4, every single one, all the exam and problem solving questions. If you'd like to see anything further than that, just leave a comment in the video and I'll make a note of it. Okay, thank you very much for watching and I'll see you next time.